Now we know that primary, secondary and tertiary amines can be differentiated through several reactions, such as the carbylamine reaction. We know that carbylamine reaction is characteristic of primary aliphatic amines, which when heated with chloroform and ethanolic potassium hydroxide forms a foul-smelling isocyanates, which are also called carbylamines, correct? Similarly, the reaction with nitrous acid also helps us distinguish between the different types of amines based on the evolution of nitrogen gas or formation of an oily liquid or absence of any change in the reaction mixture. When we have a primary aliphatic amine, we have nitrogen gas evolution. If we have an aromatic amine, we have a stable diazonium salt, benzene diazonium chloride being formed. In the case of secondary amines, we have an oily liquid forming, and tertiary amines will not give any reaction. And lastly, we have one more reliable test, which is the Hinsberg test, where amines react with Hinsberg reagent to form sulfonamides, and depending on the solubility of the sulfonamide in excess alkali, we can figure out if our amine is a primary amine, a secondary amine, and if there is no reaction happening here, that means what we have is a tertiary amine. Now, you're already familiar with these reactions because we have talked about each of them in great detail in the previous videos. So what we're going to do today in this video is basically see how to apply these tests in a particular context. In this video, we are going to solve a couple of questions on how to differentiate between primary, secondary and tertiary amines using these different tests and see which type of test can be used in which context and so on. Okay. So let's look at the first question now. Alright, so here's the first question. It says we have three amine samples A, B and C, and based on these observations we need to identify their types, whether they are primary, secondary, aliphatic, aromatic and so on. Okay. So the first reaction says A reacts with chloroform and ethanolic potassium hydroxide to form a foul smelling compound. Now this is nothing but a carbylamine reaction, correct? And carbylamine test is characteristic of primary amines, especially of primary aliphatic amines. So it's given here that A undergoes this reaction successfully to form a super foul smelling compound, means that A is a primary amine, most likely a primary aliphatic amine. Now what is happening in the second reaction? We can see that B reacts with nitrous acid at low temperature to form a yellow oily liquid. Now we know that when an amine is treated with nitrous acid, if it is a primary amine, a primary aliphatic amine, then it would form an unstable diazonium salt that would immediately decompose, releasing nitrogen gas, correct? However, a secondary amine would react with nitrous acid to form a yellow oily liquid that is indicative of an N-nitrosoamine. So from this reaction we can see that B is most likely a secondary amine, correct? We have the formation of a yellow oily liquid here. The next reaction is the reaction with Hinsberg reagent, and there's no reaction happening here. Alright, so we know that Hinsberg test differentiates primary, secondary and tertiary amines based on the solubility of the product that is formed, correct? Now a primary amine would react with this reagent to form a sulfonamide that dissolves completely in excess alkali. A secondary amine would form a product that is insoluble in excess alkali, and if there is no reaction happening, that means this is a tertiary amine, where the tertiary amines do not undergo any reaction with Hinsberg reagent, and that itself is a confirmatory test here. From these observations we can conclude that A is a primary amine, most likely a primary aliphatic amine, B is a secondary amine forming yellow oily liquid with nitrous acid, and C is a tertiary amine which does not give any reaction with benzene sulfonyl chloride or the Hinsberg reagent. Alright, let's look at the next question now. The second question says a sample contains a primary amine, but you're not sure if it is a primary aromatic amine or a primary aliphatic amine. Which test can be used to arrive at a safe conclusion? Alright, so we know it's a primary amine, but we don't know if it is an aliphatic or an aromatic amine. Will a carbylamine reaction help here? Let's see. Now the thing is, carbylamine reaction is valid or most valid for primary aliphatic amine, correct? When we have a primary aliphatic amine, it forms a foul smelling isocyanide. Now if you worked with this reaction in a lab, you will know that aliphatic amines are best suitable for this reaction, right? They give absolute confirmation. Primary aromatic amines also do undergo this reaction, but it's usually slower and might require a harsher reaction conditions. the odor might be still present, but it could be faint. Okay, so basically what we can say is that a carbylamine reaction is not the best test to distinguish between an aliphatic or a primary aromatic amine here. What about reaction with nitrous acid? Would that help? Let's find out. Now, when a primary aliphatic amine reacts with nitrous acid, it forms an unstable aliphatic diazoxime salt which decomposes immediately to form effervescence, the nitrogen gas evolution here. Now, that's a very good observable change. And what about aromatic amine? Primary aromatic amines react with nitrous acid at low temperature to form benzene diazoxime chloride, which is stable. It does not immediately decompose as we see in the case of primary aliphatic amine, especially when it is carried out at low temperatures. So here there is no evolution of nitrogen gas bubbles. It doesn't take place here. And to be absolutely sure, we can perform a coupling reaction, an azo-coupling reaction, which would confirm if we have a benzene diazoxime chloride, because in that case we would get a colored product. So yes, a subsequent coupling reaction would give us 100% confirmation that we have a primary aromatic amine. But even otherwise, if all we have to do is simply compare an aliphatic amine with an aromatic amine, then this is sufficient, right? An aliphatic amine would give us nitrogen gas effervescence and aromatic amine would not give us an effervescence. It would form a stable compound here. So I would say reaction with nitrous acid seems great. What about Hinsberg test? Now, in Hinsberg reaction, primary aliphatic amines would react with benzene sulfonyl chloride to form a sulfonamide that is soluble in excess alkali. But if we had a primary aromatic amine, this solubility in excess alkali may be slightly different because of the presence of the aromatic ring. Basically, both aliphatic and aromatic amines would react with Hinsberg reagent, but the solubility may be different or may slightly vary depending on the presence of the aromatic ring. However, this difference in solubility may not be very large. It may not be sufficient to distinguish between the two. So what I'm trying to say here is that while Hinsberg test is excellent for distinguishing between primary, secondary and tertiary amines, it does not provide a clear differentiation between primary aliphatic and primary aromatic amine. Because at the end of the day, we can see that they follow similar reaction pathways, right? And the solubility characteristics may not be so large as to make a substantial difference. So let's look at one last question now. So here we have 3 amine samples X, Y and Z, and we get the following results with each of these reactions. So what we need to do is, based on these observations, we need to identify the type of amines X, Y and Z. Okay. So let's look at the first reaction, carbylamine reaction. It says X produces a strong foul smelling compound. So that means X is most likely a primary amine or a primary aliphatic amine, to be more specific. Correct? Y does not produce any odor, which means Y can be secondary or tertiary. And Z produces a mild odor. Okay, the fact that we are getting the odor means it has to be a primary amine, but since it's a mild odor, it is most likely a primary aromatic amine. Correct? Because if it's an aliphatic amine, we would get a strong foul smelling odor. Alright, let's look at the next reaction, reaction with nitrous acid. X evolves nitrogen gas vigorously. So this once again confirms the presence of primary aliphatic amine, correct? Y shows no reaction and remains unchanged. So this means it has to be a tertiary amine. Why? A secondary amine would react with nitrous acid to form a yellow oily liquid, remember? So yellow oily liquid corresponding to N-nitrosoamine would be formed if we had a secondary amine. So from here we can confirm that it is not a secondary amine but most likely a tertiary amine because there is no reaction happening. And Z forms a stable solution with no gas evolution. So this again points towards a primary aromatic amine, saying that the stable solution is most likely a benzene diazoxime chloride, correct? It's again pointing towards a primary aromatic amine here. Now the last test is Hinsberg test. It says X forms a soluble product in excess alkali. So yes, once again confirming our primary amine, primary aliphatic amine. Y does not react at all. So this again confirms our tertiary amine. If Y was a secondary amine, then it would form an insoluble product in excess alkali, correct? Since it does not react at all, that means it is pointing towards a tertiary amine. And lastly, Z forms a slightly cloudy and slightly turbid solution. Now this is interesting because the formation of a slightly turbid solution means poor solubility. It means that the amine is not completely soluble. Amine is not able to completely dissolve in excess alkali. Now that again points towards a primary aromatic amine, because you see the presence of an aromatic ring can affect the solubility properties and sometimes leading to a less soluble sulfonamide. So it is this decreased solubility that we observe as a slightly cloudy or turbid solution. And you can see that this observation kind of agrees with our other observations that we have seen from the carbylamine reaction and nitrous acid. So what do we conclude from this? We can conclude that X is a primary aliphatic amine, Y is a tertiary amine, and Z is most likely a primary aromatic amine. Now we can perform an azo-coupling reaction to be absolutely sure, but don't worry about it. You will learn about it in detail in the subsequent videos. But for now, these seem to be our conclusions.